Hi guys, I'm Monica. I welcome you all to my channel Aerocar. In the previous video, we had started with the types of flows wherein we discussed continuum versus free molecular flow, and then we also discussed about inviscid and viscous flows. Proceeding further, we will discuss a few more types of flows. So without any further delay, let's proceed further. So here we have incompressible versus compressible flows. Now, as we can see, when I say incompressible, it means a flow in which density is constant. Now, but the question arises, do really such flows exist wherein we can see that the density is constant? So, the truth being that these flows do not really exist in nature. They don't exist really in nature. But then, as we said for inviscid flows, if they do not exist, then why are we studying them, or why have they come into existence? So here's the answer for that, as we said, incompressible flows do not exist in nature or do not occur in nature. But there are few aerodynamic problems where we can consider that the flow is incompressible. So what can be those aerodynamic problems where we can model the flow as incompressible? So the first one is homogeneous liquids. So wherever we say the liquids are homogeneous, in those cases we can consider that the flow is incompressible. So this is the reason most of the hydrodynamic problems that you see, these hydrodynamic problems, these are considered as incompressible. That is where rho is equal to constant. Now, there is also one more thumb rule which we usually follow with the flow of gases, that is with respect to Mach number. Now, what is the term Mach number? We will discuss about it in the further coming up slides. So whenever I say that the term Mach number is less than 0.3, I will assume that the flow is incompressible. This is the second case where we see that the flow is incompressible. So this was all about incompressible flows. Vice versa is the compressible flows, where density is a variable, that is rho varies from one point to another point. Where can we observe these compressible flows? Mostly the high speed flows are considered as compressible flows, where you can find density varying from point to point, and there is a wide range of densities that you find in the high speed flows. So this was about incompressible versus compressible flows. Proceeding further, how we can classify the flows, that is based on the Mach number. Now, as I used the term in the previous classification of compressible, incompressible, that is the Mach number. So this Mach number, if we have to define it mathematically, I can write Mach number as velocity of the object by speed of sound. V is the velocity of the object and A is the speed of sound, and M is your Mach number. Now, based on this term called Mach number, we have another various classification of flows, and let us have a look. What are they? The first one being the subsonic flow. As the definition says, now I can call a flow as subsonic flow if my Mach number is less than 1 at every point in the flow field. So what we are going to do here is, we have considered a airfoil, and the lines that you are able to see here are the stream lines which we usually use to denote the flow field, how the air is flowing around any object. Now whenever I am denoting this line as a straight line, which means there are no disturbances and the flow is going steady and uniform, this is what my streamlines are indicating over here. So this line is known as a stream line. So we are considering an airfoil over here, which is a cut section of your wing. Let us say the flow is coming in this direction, and we will introduce one more term over here, that is M infinity, which I can write it here more clearly as M suffix infinity. This M suffix infinity or M infinity, we call it as free stream Mach number. It is named as free stream Mach number. Now, it is coming with some free stream Mach number, the air, it is coming with some free stream Mach number towards my airfoil. Okay, I say that this free stream Mach number is less than 1. Now here the free stream Mach number is less than 1. On the contrary, we have one more point to be said, that it is not compulsory that it is going to be less than 1. That is, when the air is coming this way, let us consider at this point it is less than 1. But it is not necessary that it will be less than 1 till it crosses the airfoil and surpasses the airfoil. Yes, so there can be changes in the Mach number. So the flow field where at every point my Mach number is less than 1 is known as subsonic flow. Proceeding further, we have the second type of flow, that is the transonic flow. Now, when I say transonic flow, it is a mixture of two types of flow fields, where you can see two different types of flow fields. So let us see how. You can see airfoils. There are two airfoils that I've sketched over here. Now, we know that when the free stream Mach number is less than 1, we call it subsonic. But if in point as the flow is proceeding, what happens if the Mach number is approaching 1, that is unity? If the Mach number is approaching 1 and then eventually it becomes greater than 1, then I can call that flow as supersonic, which we are going to discuss after this. So eventually, if the Mach number is becoming greater than 1, I will call that as supersonic. So as you can see, the airflow is coming from here, and these are the pockets where we see that the Mach number is becoming greater than 1. Now this flow is terminated by shock waves, and once the flow is terminated, again behind the shock waves my Mach number becomes less than 1. Here you can see another diagram. There are these two lines in front of an airfoil which are formed. This is known as bow shock or bow shock, what do you call it as? So what happens is, now if I'm going to increase this Mach number even more greater than 1, that is, my free stream Mach number is crossing 1. Here what we see, that it is at 0.8 and it is maximum 1, and it is again going into the subsonic region. But here what I am doing is, my free stream Mach number is itself increasing, that is crossing 1. So in this case, what happens? A bow shock is formed in front of the body. Yes. Now, when my flow crosses this shock, the free stream Mach number again becomes less than 1. So eventually, as the flow proceeds, there will be the fluctuations in Mach number. This keeps changing. It can also happen that this flow, as it proceeds further, it will go to a lower supersonic value over the airfoil. And what happens, because it is becoming again supersonic, there are weak shock waves forming at the trailing edge of the airfoil. The end point, this end point is known as the trailing edge of the airfoil. So here you can see the weak shock wave is taking the form of a fish tail pattern. Now, such flow fields where I am seeing both mixed region, that is, I am seeing that the flow is subsonic in some places as well as it is supersonic in some places. Such flow fields are known as transonic flows. This was all about transonic flows. Let us proceed further with the supersonic flows. Now here what we have done is we have considered a wedge, a corner shaped wedge which is of angle theta. This is your wedge angle. Now here you can see I have sketched two lines. This is my streamline where the flow is going. There are these two lines which are attached to the corner. Any idea what can be these two lines? Let us have a look. Now, here my free stream Mach number is going to cross 1.2. So, whenever I see that my free stream Mach number is greater than 1 or 1.2, I call it as a supersonic flow. Now, the supersonic flows are mostly characterized by the term called shock waves. So, what you can see here, these two lines are the shock waves. We will discuss in detail as we proceed further with our aerodynamics learning about shock waves and what are these shock waves and how do they affect the flow. We will learn as we proceed further. So now you can see as there is a shock wave forming over here, there is a discontinuity in the streamline after it is crossing the shock wave. Whereas if you observe the same in the subsonic flow, there is no discontinuity in that streamline. So this is what happens in the supersonic flow. There is a discontinuity across a shock, and this type of shock is known as an oblique shock. There are various types of shocks. So as we proceed with the course further, we will be discussing about these different types of shocks. As previously we saw there was a bow shock, now we see that there is an oblique shock. We will be discussing it further. In this case, what happens is behind this oblique shock, the flow remains supersonic. That is, the Mach number is still greater than 1. The lines, if you can see here clearly, what I've sketched is known as an expansion fan, which is one of the type of shocks. It comes under the classification of shocks. It is formed at the trailing edge of the wedge. The profile that we have considered here is known as a wedge. The last type of flow that we have is the hypersonic flow. Now, we saw subsonic flow where m is less than 1. Then we saw transonic flow where we have a range of Mach number. Then we saw supersonic flow which is greater than 1 over 1.2. Now we have hypersonic flows. According to an arbitrary thumb rule, it is considered that Mach number greater than 5, the flows where Mach number is greater than 5, are known as hypersonic flows. But there are also some physical behaviors, as we saw. We had a bow shock in transonic flows, and then we had an oblique shock and expansion fan in the supersonic flows, right? So now in the hypersonic flows, we have something called the physical significance known as a thin shock layer. Now, what is this business of a thin shock layer, or what is this shock layer? So what happens is, as we further increase the Mach number, that is beyond 1, 2, 3, as I said, beyond 5, what happens is the shock wave, which we saw as an oblique shock wave, it starts moving closer to the body. And as this shock moves closer to the body, the strength of this shock increases. There is an increase in the strength of this shock. And that is why we call this layer, what you can see between the object and the shock, the layer that is there, we call it as a thin shock layer, as it is coming closer to the body, and also the strength of the shock is increasing. So this is known as a shock layer. Now, what happens in this shock layer is there is an increase in temperature, and the temperature increases so much in this shock layer that we can observe chemical reactions taking place, and also the oxygen and nitrogen molecules start to dissociate in this shock layer due to the rise in temperature. So this flow where Mach number is large enough that we see viscous interaction, that is, there is a viscous layer forming here above this body, and it interacts with this shock layer. Or another symptom or sign is when we see chemically reacting flows around an object, we say that the flow is hypersonic, because all these chemically reacting effects and the viscous effects are dominating the flow, and where the flow where these dominating factors are more, we call that flow as hypersonic flow. We will be further discussing more about hypersonic flows in the future. I will be uploading a separate series on hypersonic flows, where we will discuss a lot of things about what hypersonic flows are, where we see their applications, and all such sort of things. So on this note, I end this video of types of flows over here. Thank you for listening. Stay tuned.